Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 Continued, Molecular Polarity. We've already talked about polarity within a single bond, but now let's talk about polarity through the whole molecule. Molecules that have a partially positive portion of the molecule and a partially negative portion of the molecule are referred to as dipoles, the two poles being the partial positive and the partial negative side of that molecule. In other words, there might be some atoms that are more electropositive, some that are more electronegative, and they would produce a potential dipole. So it's easy to spot possible polar molecules. The number one tip-off is if the central atom has lone pairs, well then the other atoms can't be symmetrical around the central atom. And in that case, it will always be at least a little bit polar, maybe very polar. So examples of that are water, H2O, and the oxygen has two lone pairs on it, and therefore this molecule is bent shape, and the hydrogens are electropositive, the oxygens is electronegative, and they each form dipoles, but they are not opposite each other because the molecule is bent, and it's bent because of these lone pairs present. The other way that you can tell possible polar molecules is if the outer atoms are not all the same. If any one atom is different, there's no way they could balance each other in terms of electronegativity. So here are two more molecules, Boron Trifluoride, and the last one is carbon with 3 fluorines and 1 bromine on it. And neither of these central atoms have lone pairs. So we have to look at the outer atoms surrounding them. Well, you'll notice the third molecule here, the boron, has 3 chlorines surrounding it in a symmetrical fashion. So even though these bonds may be very polar, they all balance each other in a very special way. And before we go through that, the more precise way of telling polar molecules would be to tell, first of all, if there are polar bonds, which is a given. You have to look for polar bonds, and that the symmetry does not cancel the effects. And that's another way of saying that there are lone pairs that break the symmetry, or there are different kinds of atoms around the central atom that break the symmetry. So if we look at the water, for instance, we have two electropositive hydrogens that are in bonds with the electronegative oxygen, and therefore since these two aren't exactly opposite one another, they don't cancel each other out, and you have a net polarity in that water. If you look at the second one, the nitrogen trifluoride, here we have 3 very electronegative fluorines pulling electron density away from the nitrogen, but the 4th position is occupied by a lone pair, and therefore they can't balance off each other. They can't even up. They're not symmetrical around the nitrogen, and that would also be electronegative. The third example where there are no lone pairs is the boron with 3 chlorines, and since there are no lone pairs, the chlorines surround the boron completely symmetrically, and even though each of those 3 bonds is very polar, they balance each other out. They all are fighting to pull away from the boron evenly, and as a result, there is no partially positive portion of the molecule and partially negative portion of the molecule. You can't draw a line through it and say the left half is more negative than the right half, because the partial negatives surround the partial positive very symmetrically. And the last example, that same thing would be true if all 4 outer atoms were fluorines. They would all balance around the carbon. But since one of those atoms is not a fluorine, it's a bromine, which is not nearly as electronegative as the fluorines, they can't balance each other, and therefore this molecule is also polar. So looking back at the simple rules, the central atom, if it has lone pairs, it's going to be polar. It might be only a little bit polar, but it'll be polar. And if there are different atoms surrounding the central atom, as in the last case, well then they can't all balance each other out, and then that will also be polar. So symmetry means nonpolar, non-symmetry means polar. And with that, let's look at some examples. So you have to know the Lewis structures of these. I've underlined the atoms that are central atom in each case. In some cases, you'll see there are only two atoms, and therefore there is no central atom. But the central atom is what you need to focus on, and you ask yourself, does it have lone pairs? Are the other atoms the same or different? And in the case of the first one, HF, well, it's only two things bound to each other. You can say either one is the central atom, and all of the other atoms on that side are the same, so it has to be, all the other atoms are just a single atom, so that atom is polar, that molecule is polar. The fluorine is very electronegative, and the hydrogen is much less electronegative. Water, we already showed, is bent. It has lone pairs, and therefore it will be polar, and each OH bond in water is very polar by itself. The same thing happens with NH3. This is ammonia. You could say nitrogen trihydride. The more common name is ammonia. The nitrogen has one lone pair, so that tells you it can't be symmetrical. And each of the bonds, nitrogen and hydrogen, are also polar. So knowing the bonds are polar and it can't be symmetrical tells you it's also polar. Carbon dioxide, and I will just draw it quickly to remind you, carbon dioxide has a central carbon with two double bonds to oxygens. And I will not put the lone pairs on the oxygens because they're not important. We're only focusing on the central atom. And the central atom has no lone pairs, and the oxygens are both very electronegative, pulling away from the carbon, pulling the electron density away from the carbon. But they pull away with exactly the same strength in exactly opposite directions, and therefore they cancel each other out, making the whole molecule nonpolar. Carbon tetrachloride has a similar situation. The carbon has 4 chlorines on it and we're not going to worry about the shape right now. It's tetrahedral if you are in 110. You've already learned about Vesper rules to tell you that, but the shape is called tetrahedral because it makes the shape of a tetrahedron. And you'll notice they are symmetrical around the carbon. And therefore, while each of these chlorines is pulling electron density away from the carbon in the center, they are all pulling away in a very symmetrical fashion, making this molecule nonpolar. If we look at this molecule, this has 3, I'm going to erase some of this, it has 3 chlorines, but one of the positions is a hydrogen, very much not as electronegative, not nearly as electronegative as the chlorine is. So now we have this situation where there is very little difference in electronegativity between the carbon and the hydrogen. In fact, there's just even a slight pull towards carbon. Carbon's slightly more electronegative. And now we do have a dipole that's kind of generally in this direction if we added up all those arrows. And so that is quite polar. So I will erase this molecule here. And let's look at F2. Well, F2, or fluorine gas is just a fluorine attached to the fluorine. So they're both very electronegative, about 4.0, 3.98, depending on whose scale you use. And if you look these up, different periodic tables will have slightly different numbers. Always look at one set of numbers. Don't switch between periodic tables. So they're both pulling very much towards themselves, but of course that cancels completely. So this has no dipole. The difference in electronegativity here is exactly 0, and therefore, while both atoms are extremely electronegative, the whole molecule is nonpolar. And you can see this general pattern here. CH4, this carbon tetrahydride, also known as methane, behaves exactly like carbon tetrachloride. It's a symmetrical surrounding, so that's nonpolar. Boron trifluoride, we've already looked at boron trichloride. They're symmetrical around the boron, and there are no electron pairs on the boron, so they will cancel each other and therefore be nonpolar. HCN, this is hydrogen cyanide, the thing that becomes cyanide gas. Looks like this if you draw a Lewis diagram. And while the nitrogen has a lone pair, we don't care about that right now. We're only looking at the central atom. There's a little electronegativity difference pointing towards the carbon here, and there's a bigger one pointing towards the nitrogen here. So this clearly, if you add those arrows up, they clearly point in a direction, and therefore this molecule is quite polar. The next example is OF2. This is an incredibly dangerous molecule, and so you wouldn't see it in the lab very often. Just like water, it is formed, let me get that. Just like water, it has an oxygen in the center, and that oxygen in the center has two lone pairs, and it is a bent molecule because the lone pairs take up space, and each fluorine is pulling the electrons towards it, and you end up with this net dipole. You can imagine if there was one person standing in the middle and two people were pulling this way, the person would move in this general direction. That's how you can tell what the overall polarity would be of the bond. In this case, it is quite polar. And I'll allow you to go through the rest of these. Remember, sulfur has two lone pairs on it, just like oxygen. Silicon, when it has four bonds, has no lone pairs, just like carbon. So this is like carbon, this is like oxygen. The phosphorus is just like nitrogen. It's in the same column, the same group, and therefore it will have a lone pair. The carbon, in this case, I will draw the molecule here. This is carbon that has a double bond to the oxygen and two single bonds to hydrogens. So it's symmetrical around the carbon. There are no lone pairs, but this bond is very electronegative, and this one's only a tiny bit pointing towards the carbon. So you end up with this net polarity in this direction. So this molecule, this is formaldehyde, is also quite polar. And I'll let you go through the rest of these, and you can practice on your own. I'll pause here so that you can stop it, and then I'll show you the answers. Okay, here they are. Polar, because it's bent. Symmetrical around the silicon. 3 on the bromine, but there's a lone pair on, 3 bromines, but there's a lone pair on the phosphorus. The polar bond of the carbon to the oxygen is quite strong, and the oxygen is different from the 2 hydrogens, so it's polar. And the last case, we have 3 poorly polar bonds, but they're all symmetrical, so it's completely canceled out anyway.